Okay. Yeah, okay. My name is Pontus. I'm working here at OHB Sweden as a programmer or software developer, if you like it that better. So I've been working here for like 5 years now as an employee and as a consultant some years before that. And I work with flight software development and also the mission control system that you saw in the other room. And yeah, some post-processing and data analysis too. So yeah, a bit too much actually, but I'm all over the place. So I will start with just talking a bit about satellites, about our satellite, this platform that we call Innosat. And then I will go over to talk about the actual processor we use, the processor hardware. And from there I will talk about the software, the onboard software, and how we use C++ in that, because yeah, C++ is what we use. Yeah, Harald introduced this geek factor, and I would say it's a pretty low geek factor on this, so don't worry. It's more like an overview and yeah, how we use C++. So this picture here shows the satellite, one of the satellites that we work on for the moment. So this is Arctic weather satellite, and yeah, it's a weather satellite. So its purpose is basically to give better weather forecasts in the Arctic areas, because apparently, I'm not an expert on this, apparently the weather forecasts are quite a lot worse in the Arctic areas compared to like in more southern Europe. So what we're doing right now is building like a demonstration mission. So we build one satellite, and if this demonstration will succeed, then the plan is to build a constellation with six of these satellites, six totally equal satellites. Yeah, what the satellite does, it has an instrument that is like a multi-channel microwave radiometer, and it uses that to measure humidity and temperatures, and then they put that in their very large weather models, and in the other end you get out weather forecasts, and the more data you can bring into these models, the better they get. And apparently there is a gap here in the Arctic zones and in the northern and southern zones. Yeah. So as I said, this satellite is based on this what we call a satellite, the satellite platform that is called Innosat. And we have a satellite that we launched just, what is it, 3 months in November last year. And here is a video where you can see when it's actually is released into orbit. It's just a short video. There it goes, out in the orbit. And as you can see, so MATS is quite different from Arctic weather. So yeah, they share quite a lot. But as you see, it's not, when I say when I call it like a satellite platform, it's not just some static thing that you put a payload on. You do a lot of customizations. And MATS, it's actually a science mission, and it's a Swedish satellite. It's paid by Swedish, what is it called? Swedish National, help me, SNSA, Swedish National Space Agency. And the science is done by MISU, That's the guys on Stockholm University. And it's basically, it has an optic instrument that is used to do imaging of the limb of the atmosphere to detect and make a map of kind of atmospheric waves that can be found in the upper levels of the atmosphere. So it's like it's a basic meteorological research, basically. And it's ongoing right now, so it produces science data every day. Yeah, so that's what we did a couple of years ago, because this satellite was done quite a while back. So this is like old stuff for us. And I have a picture here. Just here you can see how Mats works. It just fly, and it uses this instrument to look at the atmosphere from the side, and they make some kind of mapping of these waves. But please don't ask me too much about that, because that's basically all I know. What does it mean to have a satellite platform, since they are so different? And we have like a product manager for the Innosat platform. I think he put it quite good. So the platform, it's satellites built and designed around a set of reusable core elements. And one such core element is, of course, the software. Because we have like a basic framework and a library for building onboard software for satellites. And we can share quite a lot of the code between the satellites. Yeah. So I just want to describe for you guys what do we have on the satellite? What is a satellite? What kind of equipment does it have? So I will just do this quite quickly so we can get into the software side of things. But I think it's good to see this just so you know what we are doing with the software. So we have different subsystems. And here you can see on the left here we have the electrical power system. This is the solar arrays. It kind of fell away. So you have solar arrays that you feed the battery, and then the battery is connected to this unit that is called PCDU. It's a power control distribution unit, and it's the unit that actually, it does what it says. It distributes the power to all these other devices and the equipment. So it contains like a lot of protections and DC-DC converters for different voltages. Everything we need to get the satellite up and running. And then on this right thing here, it's the DHS. This is our world. This is the data handling subsystem. So that's the computers. And we have a couple of different processors on every satellite. And we have this, what we call SCM. So it's the actual spacecraft controller module. And there is where you find most of the actual interesting logic, the complete controller of the satellite. And then we also have one or more of these so-called TCM computers. And the TCM, it's like a really complex, it stands for TT&C controller module. And TT&C stands for telemetry, tracking, and command. But never mind that. What it does is it actually controls the communication link against Earth. So you send stuff over to that computer, and then it will communicate with the ground. And it also it has one more important component, and it's the mass memory. And the mass memory it's where you actually put all the science data and telemetry that you eventually want to download to ground. Since we only have contact with the satellite, like a short, brief contact now and then we just try to download as much as we can. And everything will just accumulate in the mass memory. And hopefully you can download faster than you fill it up. And then we have some other subsystems. I'm not going to talk about this. This is like the subsystem that this computer is controlling. So it contains like a transceiver and radio frequency stuff. Then we have a thermal control subsystem, which consists of different heater lines and thermistors. So you can keep track of all the temperatures and if you need some heating somewhere. And then you have this quite large subsystem that we call AOCS, Attitude Orbit Control Subsystem. And this is all the devices that we need to actually control the satellite. And when I say control, I mean control how we are pointing the satellite and keep it stable, and also change the orbit if we have electric propulsion on it. We don't always have that. So I will just quite briefly go through what this is, the different devices, and I think most of them speak for themselves. Magnetorquers or torque rods. They are used. They create like a magnetic dipole that interfaces with Earth's own magnetic field. So you can use that to for attitude control. And when you launch the satellite, when you release it into orbit, it often tumbles a bit. It's not like it's very fast, but it tumbles. So you need to stop that tumbling, do a detumbling. And that you can achieve with the torque rods. And you can also use it for just stabilization to get a good pointing, a stable pointing. And to use the magnetorquers, you also need a magnetometer. So you need to measure the current magnetic field. So those two kind of need each other. And then you have star trackers, one or more, and they are used to, it's just a camera, and you take a picture of the stars, and then you use that to look up some kind of star map, and then you use that to get the attitude or orientation of the satellite, so you know exactly how the orientation is. Then you have the reaction wheels, and the reaction wheels are, of course, also used to move the satellite around, and you can use them to provide a 3-axis attitude control with very high pointing accuracy. And and then I got this question here before: how do we know the position? We have a GPS. They work in space too. So from the GPS, we get the position and the speed of the satellite. And then we have the sun sensors that help us detect where the sun is, so we can turn the solar rays against the sun. And finally on this list, we have the EPOs, the electric propulsion units. A question?
Yes.
Oh?
Why do you need to know where the sun is? Can't you just calculate that from some calendar and the orientation?
Yeah, we can, but that's more complicated. It's easier. It's really simple. The sun sensors are really simple. You just get like intensity, and then you have them on each side, and then it's easy to just calculate where the sun is. Then you don't need to do some calendar lookup or anything. So yeah, it's simplicity.
How do you test the magnetorquers and reaction wheels and such things? You throw one up there and see if it stops.
I think they are pretty well proven technology, I don't actually know how. We can turn it on and see that we get some magnetic field that sounds reasonable, but I don't know how they measure them, how they prove that they are working correctly. It's a bit beyond my knowledge. But this is basically it. This is what we have that we work with, and then also what we can't see here. This is just a platform. Then you also have the payload, the actual. I mean, the payload. That's the important part of the satellite. But this is everything here is to provide the payload to help the payload do what it should do, basically. This is the computer that we have. So the onboard computer, or OBC, if you want to talk like that, we buy it from a company called AEC CloudSpace. It's called Sirius, and it's a 32-bit processor, a fault-tolerant processor. And the architecture is Leon, the Leon architecture, and it was actually built by ESA long back ago. But then nowadays there's a company called Geisler that is taking care of this platform. And it's actually based on the Spark architecture, Spark V8. So this is what we have in our up-and-coming satellites. In the ones that we already fly on this platform, they actually run OpenRISC, which is a kind of dead architecture, it feels like. Yeah, but it works. And yeah, you can read for yourself. It has a FPU. We have a decent clock rate. I mean, your PC is much better than this, but it's what we need up there. We have like 128 megabytes of RAM memory, but all the memories, I think all memories are EDAC protected. EDAC stands for error detection and correction. So that use half of the space. So we can only use half of the memory, so 64 megabytes, which has been more than we need so far, actually. Then we have a level 1 cache that's much smaller than on your PC. We have a special memory, a non-volatile RAM, that we can use for stuff that we want to store between reboots, basically. So it's just a very small memory, 32 kilobytes, and we can only get half of it, 16. And then the board support package, the underlying system uses like 4 or 5 kilobytes. So we actually only have about 10 kilobytes. But it's actually more than we need. So yeah, we're happy. We have a system memory, NAND flash, 4 gigabyte, again, EDAC protected, so we only have 2 gigabytes. And the only thing we use that for is the software images. So it's quite a lot of space for just that. But the bootloader, I will not go into that because it will take forever. But the bootloader it actually uses the complete space. We have like 6 different copies of the software image, and we have 3 of them that you can't even, they are read only, so you can't flash them when the satellite is in space. And then we have 3 that you can update, and they are spread out over the whole memory. So if the memory gets corrupted somewhere, we can somehow get back to business. And the bootloader has like a sequence when it tries to boot all the images, and if it fails, it just tried next one, and if the last one fails, it tried to boot it anyway and see what happens. So yeah, that's how it works. We have some interfaces for the communication between the different computer system. We have SpaceWire, which I guess you haven't heard about if you haven't worked in the space industry. it's a serial communication network or bus that is quite simple. So it doesn't take so much space when you implement stuff like in a FPGA. This whole computer is actually on a FPGA, so it's not the ASIC. We have some different UARTs, and we have a bit of GPIO. And this whole computer is quite, as you can see, the nominal power consumption is just 1.3 watts. So it's quite neat. And it's a small one. I can show you. Here's a picture of it. This is one computer. This is the complete system on a chip. And then when you have more than one, then you just stack them together. So you get like a, that's when you have stacked all the one together, that's your DHS, your data handling system. So that's everything I will say about hardware. So let's talk about software. Yeah.
You mentioned that you can do software updates.
Yeah.
Which kind of transfer speeds do you get to this?
On the uplink, it's pretty slow. I think it's around 64K or something, kilobits.
Do you do?
Well, hopefully never. We have Mats has been up for 4 months now. We haven't done any update yet, but we will do one maybe in a couple of months. So it has been running for 4 months without the reboot now. So yeah, but we have found one issue that we need to fix. So yeah, we will soon send up a new software. Yeah.
So you mentioned this is all running on an FPGA.
Yeah.
I would expect that, like, is the volume that you need just not big enough?
Exactly. Yeah.
Because you could save some energy, I imagine.
I mean, if you have a proper ASIC, it's much faster. I mean, this runs in 50 megahertz. If you have the same one in ASIC, it probably runs a couple of hundreds megahertz. I mean, everything is better with ASIC, but the volumes.
What's special about it that you can't use something off the shelf? Is it you can't get the fault tolerance from
No, I would say it's the fault tolerance, because that's kind of a big thing. So it's radiation hardened, and that means it goes both on like which materials you use, but on a more logical level, you do a lot of stuff. You have like you EDAC everything. You have like scrubbing of the RAM all the time, trying to find bit flips, and you have like parity checking on everything, and also the complete processor is constructed with something called TMR, triple modular redundancy, and it's a kind of majority voting system. So all the important stuff is made like 3 times, and then you take the decision with the majority voting. So yeah, but at the same time, I know that the whole CubeSat world, they say send up anything, and it seems to work sometimes. So yeah, the CubeSat world they're running their own thing. So we are a bit more old space than they are. I don't know. I mean, people have sent up like Raspberry Pis, and it seemed to live for a while.
Do you have statistics of how often you get bit flips?
Not really. I mean, if we would get a bit flip on some important, if like in the instruction cache or in registers, then you would immediately get a reboot. And we haven't had a reboot, so in 4 months there haven't been one. But this, the MAT satellite, it's on 600 kilometer, and we had one before that was on 1200 kilometer, and there we actually saw reboots from time to time. So we had some bit flips going on there, but it's quite more harsh environment on 1200 kilometer. So yeah, I mean these really big satellites like James Webb, and they are really far out in space. I'm not sure how they accomplish that, to be honest. I guess they have like multiple processes and do this majority voting on complete processors or something.
Or just really fast reboots.
Yeah, that too. Yeah, we have pretty fast reboots. I mean, it takes like I don't know, 2-3 seconds.
Or lots of lead. If you have the EDAC memory, why do you still need to reboot? You can't correct
Well, yes, it can do that if it's like in non-sensitive areas. But if you have like a bit flip, not in SD-RAM, but in like registers and stuff closer to the processor, then the only thing you really can do is to reboot, because I don't know what you should do otherwise. But in the RAM memory, you can have bit flips, and it can be corrected.
It's not corrected memory, it's entirely protected or something like that, or
Sorry?
it's not error corrected memory, but so you can correct where you can detect
Yeah, no, you correct also, but you can only correct a certain number of bits. So if you get too much errors, then you can't do anything. And I think if you get like a bit flip in the memory areas where you actually have instructions, then I'm not sure about this. Then I think it will do a reboot just for safety, if it can't fix it.
So how important is temperature? I guess when the sun is heating, it can be quite hot.
Yeah, I mean the temperatures can be very high and very low, so it's quite demanding on that point. So yeah, it's really important. So that's why we need to have the heater lines and measure this very carefully and try to stay in certain areas of temperatures to keep things working. I mean, really not an expert on the thermal side of stuff, but yeah. When we have like early on with a satellite, we have like one guy just monitoring temperatures, basically, to see that everything was done correctly, and yeah, tune stuff if he needs to. So yeah, that's really important. And
How much power do you get from the
Sorry,
solar panels?
we don't have so much time.
maybe we can go back to this later if we have time. I will just talk a bit about software before. So yeah, what does the software do? Yeah, well, you can guess a bit, and you have seen the hardware. So yeah, so attitude and orbit control. That's the actual control logic of the satellite. So that's of course a big part. Then we have something called FDIR, Fault Diagnostic Isolation and Recovery, and that's the part of software that's constantly monitoring everything and try to find if there is something strange. And if it finds it, if it diagnoses it, then isolate it, and then it tries to do various recoveries. And a recovery often means like turning a device on and off. It's like on Earth. And if it's something really, really bad, then it will do a reboot. But we don't want to do reboots, so we try to avoid that as long as we can. We have the thermal control, the monitoring of the thermistors and controlling of heat lines. We have the power handling, turning units on and off, and system handling. That's the satellite is always in a certain system mode. So when you just launched it, when it is released into its orbit, it's in standby mode. So everything is turned off, and then they try to make it a bit stable, and then you go to safe mode. Still, much of the devices are turned off. What you try to do in safe mode is basically just turn the solar arrays against the sun and just keep the battery loaded. And then you can start trying to test if all the devices work nice. So that the system handling part is just handling this state machine, basically. We have something we call unit handling, and that's about, since we often have redundant devices, like we have multiple reaction wheels, multiple GPS receivers, and if a device gets in such a bad state that we really can't do anything, we try to reboot, nothing helps, then we can switch over to the redundant device and run from there. We do the payload is mostly autonomous. It takes care of itself, but sometimes we need to support it a bit, like give it some time or do some configuration. And then we of course have the software upload that we were talking about. And then we have a system. I will talk a bit more about this later. You can queue up a lot of commands, basically. So when you have a contact, you just send up like 1,000 commands, and you can make them fire when you're in the right position or in the right time. So it's a kind of command queue system. And housekeeping, that means just that we try to receive all telemetry we need to see that everything looks fine. And then we have also the mass memory storage. So there's quite a lot of tasks for the onboard software. So next, I will just try to describe a standard that we use, and the reason I would like to introduce this for you is that this is actually a quite important thing, because it really affects the complete architecture of the software. So I will just mention this briefly. So there is a standard called Packet Utilization Standard, or PUS standard. And it's basically a document, 656 pages long document, almost diabolical, but not really. So it's a standard organization called the European Corporation for Space Standardization that writes this. And they have taken like decades of spacecraft experience and put down into this document. It's actually a really good document. So it describes a certain way to operate your satellite or build your software architecture. So it describes a packet switching communication between ground and space. It describes the binary format for commands that we send up and for the telemetry packets that we receive down. And it defines a software architecture that they call it application processes, but it has nothing to do with like operating system processes. I will talk more about that later. It defines a parametric system that is used, and it defines a long list of various services that you might need to operate your satellite. So it can be like device access service that makes it so you can access directly some device just to do some debugging or something. It defines like housekeeping and event reporting services, time management, even a test service that's like a ping server almost. So you can check if everything is alive. So yeah, it defines about 20 of these services. And they call it a standard, but it's not really a standard, because it's more like a recommendation because quite a lot of stuff is mission specific. That's the most that's the most used word in the whole document, I think. Almost everything is mission specific, but it's quite nice. So why do we use this? Well, as I said, this is a well-proven software architecture for building space software, and actually quite a lot of mission control systems on ground is designed and based around this POS standard and the POS services. So it kind of makes sense to actually use this. And as I said, it's a really good thing. So it's not something that we need to have and don't want to have. So I was mentioning this. What happened here? So this is a keyword here, the application process. An application process is an element of the space system that can host one or more sub-service entities. So you can think of this more like an endpoint, where a part of the satellite software where you can actually send commands and get telemetry from, and you can add services to it, or like a module, a software module. That's what it often turns out to be. This is just a screenshot from the standard. I just want to show you here how crazy it is, because I mean, it just states this is a binary interface. So it just states that something is an unsigned integer or some enumerated value. Here we have some defined stuff, and then you have optional stuff. So yeah, it's not a standard; it's a recommendation, more or less. And now I will show you this, and we will stay here for a while. I will try to zoom in on this. I don't know if I can do that without the mouse. How can I do that? Ah, there we go. So I will describe the software architecture that we have, and this will touch a lot of areas like real-time operating systems and yeah, a lot of stuff. So let's go from, I've tried to do this in layers. So this is the low-level stuff, and then you go up to the application layer. So at the bottom here we have the BSP, the board support package with all the drivers for all the stuff, for the UARTs and the SpaceWire and the non-flash and everything. And this is something we get from our supplier, but we have a full source code for everything, so that's good. So from now and then we actually apply our own patches here because we not always agree on interfaces. And then we run a real-time operating system called RTEMS. Have you heard of RTEMS? Is that no? Now it's also very. It's from the beginning. It was a military real-time operating system, and during that time it was RTEMS stand for Real-Time Executive for Missile Systems, but then it went open source and was kind of rebranded, and it was picked up by the space industry. So now it's Real-Time Executive for Multiprocessor Systems. So they try to clean away the military roots. But it's quite popular in the space industry, especially here in Europe. But for example, it's used on the Perseverance Mars rover and on quite a lot of Earth science satellites. So we actually don't use very much from the operating system. We basically, when we go up here, this is. I need to go up a bit more so you can see. So this is a component called Spartan. This is our framework library for building flight software for satellites. And we have like a sub-library or help library called RTS. It stands for Runtime System, which basically wraps all the operating system stuff And it's not much that we use. RTEMS comes with like a task handling system, and a task in RTEMS is basically a thread. And we get the thread synchronization stuff like semaphores and events. And we have some sense of time. We can get like ticks and stuff. So this part can be ported to whatever you need. So we have ported it to Linux and Windows, and we can use that for running unit tests and building simulators and stuff. And then we go up here in the layers. So Spartan is it has like two sides. It's a Python framework that we use to generate code. We do quite a lot of code generating. I will talk a bit more about it later. So it generates C++ code, and it also generates this SDB. It's a spacecraft database. It's basically a database that describes the interface between ground and space. So it's used by the mission control systems on ground. And then we have the library part. And this library basically implements this POS standard I was talking about. So together with this library and the POS standard and the generated code, we get quite much of the onboard software. I can show you. Let me see. Maybe I should show that later. I have a slide later about the code generating. So I will continue up here.
What's actually running on the satellite? What's not running?
Sorry.
Well, it's on the...
Everything here is running on the satellite, except the only thing that's not on the satellite, it's this. And the Python code is not running on the satellite. So this is a framework for when you're building stuff. You generate code that, you see here, you generate C++ code that will end in the satellite.
You're not running Windows on the satellite?
No. So it's just for testing and for simulators. Don't scare me. And then we come up to the, if you remember, we had like two computer systems. We have the SCM software, the spacecraft control module, and we have the TCM. So this is grayed out here. This is actually a black box for us. This is the software that we get from our supplier. But we have started to actually bring it home and write it on our own, because we don't like black boxes. It causes us problems. But this is the thing that we work with most of the time. So at the bottom here we have HAL, the hardware abstraction layer, and it's an abstraction against the drivers basically. And then we have two layers, the resource layer and application layer. And all of these boxes here are what I called application process before in this POS standard. So these are like, from the ground perspective, these are like, they're like modules that you can communicate with directly from ground, from the mission control system. So you can send commands to this one or to this one. You can get telemetry from them separately. And the difference between those two is the resource layer is kind of high-level drivers. So we have like one for the star tracker, and this contains all the codes that we need to write to integrate the star tracker in the onboard software. And it's the same for all these ones. So when we write this, we're reading a lot of manuals and data specifications, trying to understand how they work and how we should communicate with them. And then here is the actual application layer of the satellite. So here is where the stuff really happens. And this maps, as you see, it maps to the different functions that I showed you before. So what's interesting here is that this AOCS, that it stands for Attitude and Orbital Control System, it's actually this is actually done in it's model-based designed, done in Simulink. And for some reason in space industry, this is like other guys. It's not us. Model-based design, they don't count as software guys for some reason. So they do their models, and then they generate C code, and we bring in the C code into this. Everything else here is C++. Yeah, I think that's enough. Yeah, we have some utilities, and we have like some transport layer stuff for parsing different protocols and stuff. A lot of help classes for that. And then we have, okay, so this is also on the ground. This is not on the satellite. So we have two different simulators. We have a system simulator that runs the complete satellite like on a PC. And then you have a HEAL simulator, a hardware in the loop simulator, where we actually run we run the SCM software on the proper unit, and then we run like models for the different devices. So we can do stuff like do proper tests of the computer, the real flying computer system, like load tests and stuff like that. Yeah, let's see. Was there something more? Yeah, and also we of course have the payload software, but the payload software is always written by the payload, the guys constructing the actual payload. So it's kind of independent of the rest of the software.
Does it run on its own CPU?
Yeah. They have their own, and sometimes they have their own transceiver too. So yeah, it can be really standalone. And this, I also, just for clarity, we have this boot ROM, but it's actually on the actual system on a chip. It's on a ROM there. It's the bootloader that I described a bit before. So this is the basic architecture of the Innosat onboard software. So it's quite. I mean, if we don't need to run RTEMs. We could be able to run some embedded Linux. We haven't done that yet, but it's possible. Or we could add another box here with I don't know, VxWorks or anything. So it's quite modular, and you can do a lot of customization. Yeah. So let's talk about what's in those boxes. So, yeah, this is our world. We are a bit behind. So before my time here, they sent up a satellite called Mango, and the complete software was written in C, and they had like a lessons learned, and they weren't really happy. So they thought, okay, maybe we should try C++. And this was around 2013, before I was here. And then there was this new shiny thing called C++ 11, which made C++ like a new language. So they decided to, yeah, we're going to use that. So we were probably the first satellite doing that. And also, I mean, all embedded programmers are always skeptic about new stuff. Using the STL, that was also unheard of. But we decided to, we're going to use C++ 11, and we will will have extensive use of the standard library, because it's pretty good. Let's face it, it's not the 90s anymore. So we've done that, and we kind of use everything in C++ 11. We really went all in C++ 11. I can show you, since this is an embedded system, after all, there are some kind of limitations and challenges for us. I try to summarize it here. So yeah, it's a real-time system. It's not hard. It's not like anyone dies if we miss a deadline, but it's kind of semi-hard, because we don't want to miss our deadlines, because then we get like noise in the controlling, and then it doesn't look too good, and then the scientists will get mad at us, because they see that in their analysis. Yeah.
No dynamic memory allocation in runtime, but STL uses dynamic memory allocation. So
yeah.
How does that work together?
Yeah, exactly. So, I mean, not the complete STL use that. So this is how we do it. So we decided, I don't know if it was right or wrong, but we decided to try to avoid dynamic memory allocation, to avoid memory fragmentation and costly allocations, basically. Because since it's a semi-hard real-time system, we need to fix the deadlines, it can be a bit limiting when it comes to STL use. So what there are a lot of stuff we don't do. We don't use containers that uses heap memory. We have our own fixed size containers for that, and it's kind of messy, because it's not always obvious when STL uses heap memory. Sometimes it just, for some strange reason, it do some kind of allocation in the background. But we have some allocation here and there, but it's not a big problem. I mean, there are quite few allocations in runtime. And when I say runtime, it is okay to actually use allocation in the startup phase. So we have some like STD vectors in constructors and stuff, just setting up something. That's okay. But when everything has booted, it should be pretty stable on memory usage. That's the idea. And yeah, this system, I mean, it could be running for years without the reboots. So we want it to be stable. We don't use exceptions, or we actually, I have started to cheat a bit. So we have actually some exceptions nowadays, and it seems to work okay. I mean, we don't use, when I say exceptions, then they really are exceptions. It's not like some kind of signal handling. If we throw an exception, it should really be an exception. We used to have them turned off completely by the compiler, but somehow that flag disappeared. I don't know. I'm not really sure when. And suddenly we had kind of exceptions. So yeah, I don't know what I should say about that. There are a few exceptions, but we tried not to use them so much. I will show you a slide after this one, actually, about the cost of exceptions. So we don't have a file system, but that's not really a problem. The only thing is that we can't save stuff down to some temporary file. That's about it. So yeah, it's really not a limitation. Then we have this. We are pretty stuck on C++ 11. We are actually, our cross compiler is based on GCC version 4.8.3. So it's like 10 years old. And our supplier just refused to give us a new one. And I've even tried to build one toolchain myself. But then, even if I should succeed with that, I don't think we can use it because we need to be able to say that it's really tested. I mean, I can't say that if I just build something myself. So GCC 4.8.3, I think it has full support for C++11, and it has some C++14 support. So that's where we are. Sometimes we do backporting of nice features that we miss if it's not too hard. So we have some like C++17 thing in our own namespace when we get jealous.
Why is the CPU based on Spark again?
Because,
Would it be easy, right?
I mean, because that's what we get from our supplier. I mean, there's no good reason. Leon it's very popular in space industry. It's very well proven. It has all this fault tolerance stuff. I guess that's the reason. Yeah, and the next thing here, limited. This is an insult to the guys here who really do something on small microprocessors. I mean, it's okay. It's a 32-bit processor with 50 megahertz and 64 megabytes of RAM. I mean, it's okay. It's kind of small if you're used to develop on PCs, but for embedded system, I guess it's okay. Yeah, and since we use Spark, we have a big endian byte order. It's not really a problem. It's just something to be aware of. Because since we're communicating with ground, we need to, make everything readable, so we don't switch the byte order suddenly. I mean, this C++ that we're stuck. Do I miss something? Yeah, I do, but it's okay. There are quite a lot of stuff from later C++ standards that I don't miss. I mean, as I said, we do some backporting. Like, for some reason, they didn't have make unique in C++11. It came in C++14, so we backported that. It's like 3 lines of code. And some stuff in the algorithms library is backported too.
Optional?
Not optional, actually. We don't have that. But it's actually one of the things I miss. So then, maybe we should backport that. I don't know if it's possible. But the one thing I really miss is actually concepts, because we are quite heavy on templates. I've never done any. I've never done any proper development with concepts. I only read about it, but it seems nice. I would like to have it. We have some use of const expert, but it was so limited in C++11, since for each big standard they kind of made it more useful. So in C++11, I think you can have if you have a const exp function, you can have one line. You're not allowed to do so much stuff with it. So it feels like it got really useful maybe in C++20 or something. Yeah. Oh, sorry. I need to hurry up. It always takes. I promised you this. So about exceptions. So this is just a screenshot from Google Benchmark, and this is done. This is not done on the Spark processor. This is done on this one. So I just noticed that I just did some benchmarks, and this is like a test where I throw like a STD runtime and catch it, and it takes almost as much time as calculating a CRC32 checksum on a 256 byte array, and without using a lookup. So it's a crappy CRC32 implementation. So yeah, it's kind of costly to catch an exception.
My experience is also costs a lot of memory.
Yeah.
The size of the flash explodes when you forget the exception switch.
Yeah.
You don't have that problem.
We don't have a very big memory footprint, so it's not a big problem, but it's certainly something to be aware of, because it's not just something nice that comes without a cost. Yeah. So yeah, I'm almost done here. So I will just in the last few slides here, I will just show you some of the concepts and techniques that we use. Nothing unique for us, but something that we do that has served us well, basically. So one thing is this code generation that I was talking about. So we do like really heavy code generation. We generate everything we can. And this is a bit embarrassing. I always feel a bit embarrassed when I show that we actually use XML files. I don't know. Some of you are so young, so you don't know what XML is. It's like a horrible technique from the 90s. But it has really worked well. I can just show you an example. What we have. So this is. Sorry. Where is the pointer? There it is. So this is just an example. So this is a definition of the GPS resource. This is something that we defined how should we set up this GPS resource, the application process. So we have a bunch of parameters. We have input parameters coming from other application processes. We have output parameters. Yeah, that's either goes to other application processes or go to the ground. And the big thing here with the GPS is, of course, the position and the velocity. So this is the main information from this. Then we define tunables where we can do configuration, basically. We have calibration curves. We can have linear calibration or enumeration where we basically give certain values a name. We have like different services. Here we say that okay, you can this application service have a device access interface, so we can access the GPS UART directly from ground if we need to. Then we have a lot of reports defined here, and in each report we define which parameters it should contain, and if it should be enabled at startup, and the rate, how often it should be sent. And this will generate the code for doing all this. Then we have various commands to do certain stuff. And this will just generate like an empty function that we need to implement. We have events, and it's just another kind of report. And you can actually, they are triggered. So either you can trigger them manually in the code, or you can actually trigger them here. You can have like a triggering parameter and tell it should be triggered when it goes from a value to a value and stuff like that. So like our dear system engineers that are not programmers, they can actually go in here and do some coding. So you can decide yourself if you think that's a bad or good idea. And then at the end here we have like our scheduling tasks. So this will also just generate like an empty function that you need to populate that will do the actual stuff, the actual integration against this GPS. So that's just a small example. But we actually generate the complete scheduling for the whole SCM software. So we can just set up everything and tell, okay, this task should run at this point. It has this maximum time, and then it just generates everything for us. And also, then we don't only generate code. We generate this database, and we generate a complete web page, which is the complete ground-to-space interface. And then, of course, we have our Simulink modules that will generate C code. So yeah, we love code generation, actually. And I think about half of the compiled code on the onboard software is generated. So it's around 250,000 lines of code, and half of that is actually generated code. So for the SCM software, it's about 250,000 lines of code, and yeah, 50% is generated code. Only a few slides. What more do we do? Yeah, we prefer compile time over runtime. So yeah, and code generation is a big thing in that too. We really go nuts on templates, basically. And one example of that is that, as I showed you before, where is my mouse pointer? There. As I showed you before, this POS standard that we use, it's so much stuff in it that is mission specific. So it's kind of hard to do. How should you implement that? Then we do policy-based design. So we have like a dependency injection where we tell the Spartan system how we use this POS standard. So we can support like any kind of ground system that uses POS. If they have like some field length that's not that we didn't use before, we can just fix the policy. And yeah, so this makes use of the templates quite heavily. So yeah, we probably get a cost in compilation time, but it's okay because I just measured earlier here that a complete build on Windows where you build everything, you build SCM software, you build multiple simulators, unit tests. It's like 10 minutes, and I mean it's not often you do a complete build. You do your development, and you just build what you need to build. So it's not a big issue. And actually, when you run the cross compiler and build the actual proper flight software, it's like I don't know 2 or 3 minutes. So for me, that's not a long compilation time, at least. Yeah, so we prefer compile time over runtime. We don't do much of template meta programming because we don't have a reason, and we try to do clear stuff. We try to avoid being too obscure, basically, and we haven't had a need for it. And yeah, I think I only have one slide left. Sorry for the fast pace here. Yeah, as I told you, we're not big fans of dynamic allocation on the onboard software. So we try to manage some kind of static memory handling. And we do that by not using so much of the containers in STL. We have implemented our own static size containers. So we use std array, of course, because it's static. Then we have like our own circular byte buffers. We have a hash map, a list, a queue. We have a stack, and we have some other containers that works fine. And we do use memory pools for some of the objects, and the TC, the telecommand and telemetry packets are used everywhere. So they come from a memory pool, and they are sent through the code. It's basically everywhere, and we managed the pooled objects. We move them around, and we use the unique pointer, and we move them with std move, and then we have like when they go out of scope and you don't move it, it actually goes back automatically to the memory pool with a little help from a custom deleter. So this is something that has served us really well. So yeah, so it has managed us to have this kind of static memory software. Oh, sorry for the speed here at the end. Yeah, that's basically it. My last thing is just this. Here is almost 10 years of development in 2 minutes. So this is based on Subversion and later Git commits. So yeah, that's it. Thanks.